Here are solutions to homework set number 3 for ECE 376. This homework set looks at binary inputs, binary outputs, and timing. And the first one is for binary input. Design a circuit that outputs 0 volts and 5 volts. I turn on for temperatures greater than minus 15 C, turn off for temperatures less than minus 15 degrees C. So minus 15 degrees C, above that it turns on, or 5 volts. Below that it turns off, or 0 volts. Well, to do that, I'm going to use a thermistor, like this guy. At 15 degrees C, this is 7627 ohms. I'm going to use the voltage divider. This is kind of arbitrary. Let's just assume a 10K resistor. At 10K, this is 2.16 volts. That's really what the circuit cares about. And the way thermistors work, as temperature goes up, the resistance goes down. As the resistance goes down, the voltage goes down. So I want the voltage to be on 5 volts when it's really, really hot. So when it's really, really hot, this goes to 0. I want to compare it to 2.61 volts. The 2.61 goes to the plus input. The divider goes to the minus input. So there's your circuit. It's a comparator that turns on when the temperature is greater than minus 15 degrees Celsius, or the voltage is less than 2.61 volts. Same thing. Problem 2. Design a Schmidt trigger. In this case, I want to have kind of this type of characteristic for temperature. At minus 15 degrees, it turns on. At minus 20 degrees, it turns off. So it kind of looks like this. I turn on at 15 degrees C, turn at 20. Same procedure as before. Use a thermistor. It turns off at 10K, 10.2K. Turns on at 7626 ohms. Convert that to a voltage. Let's assume the same voltage divider we had before. The voltage that it turns on is 2.16 volts and turns off at 2.53 volts. Now I like redrawing it. I like voltage to go up as they go right. So if I redraw it, I'm trying to do this. Turn on at 2.16 volts, turn off at 2.54 volts. So over here, this is actually hot. When it gets hot, R goes to 0, V goes to 0. Over here, this is cold. Well, to design it, kind of backing up. I draw it this way because the circuit only cares about voltage. It doesn't care about Celsius or anything else. It just cares about voltage. As far as the circuit's concerned, as the voltage goes up, the output goes down, so connect to the minus input. I switch, when the output is 0, I switch at 2.16 volts. That's my offset. And the gain is the ratio. Output changes by 5 volts as the input changes by this difference. Gives you a slope of 13.4. Make this 13.4 to 1 and make it big, because this is nominally about 1K. Make that large relative to 1K, so 1.3 meg would be good, 134K is good. Just make it really, really large. The circuit actually is a little bit wrong. This is in parallel with R. That changes R. If this is large relative to R, you're only changing it by like 1%. But if you built it, it would be slightly off. I can adjust that by adjusting this voltage. But anyway, here's the circuit that gives you that Schmidt trigger. It turns on at minus 15 Celsius, turns off at minus 20. Problem 3. Now here's a tough one. Come up with a circuit that does this. For temperatures between minus 20 degrees and minus 15 degrees, it turns on. And here, just kind of curious to see what you came up with. There's a couple ways to do it. One approach is just to use two comparators. One of them does this logic, the other one does this logic. And in software, if it's greater than minus 20 and less than minus 15, then that's true. Software solution. You can also do that in hardware. This is a little bit trickier. What I'm going to do is actually have two types of logic. First one is temperature greater than -20, so this will be A. The second one is temperature less than -15, B. And the output is true for A and B. I'm then going to use an AND gate. One way to do an AND gate are diodes. So here's the first one, is temperature greater than -20, gives you this characteristic. Temperature less than -15 gives you this characteristic. If they're both 5 volts, the output is 5 volts. If either one is 0, the diode turns on and the output goes low. So that's kind of like an AND function. The output is true only if A is true and B is true. That's kind of one thing you can do with diodes. You put them together and create AND. Problem 3. That was 3. Problem 4. Design a circuit to output 20 milliamps for each diode of an RGB Prana LED. Basically output full power, full brightness. This is the voltage drop across the diode, so you just really have this circuit. I've got 5 volts when turned on. The diode drops 2 volts. 3 volts at 20 milliamps is 150 ohms. This is 5 volts. Voltage drop across the green diode is 3.2. 5 minus 3.2 is 1.8. 1.8 volts at 20 milliamps is 90 ohms. 90 ohms. This is the circuit. And with the microprocessor, then I can turn these on and off to get partial brightness, like 20% on. What I would do this. If this is on 20% of the time, it's 20% as bright. That's the software solution for varying the brightness. As opposed to 320, the hardware solution is vary the resistances. Problem 5 is design a circuit to turn on and off a 5-watt LED. In this case, I need more than 25 milliamps, so I need a transistor. So first, pick your favorite transistor. I'm going to assume a 6144 NPN transistor. It has these specs. I'm then going to build this circuit. The first part is take your LED. This is a 6-volt drop across the LED. I want full power 700 milliamps to flow. Pick that resistor for 700 milliamps. For a transistor, when it turns on, it's roughly 0.2 volts. Close to 0, but not quite. The LED is about 6 volts, so this is 6.2. Pick your power supply. I chose 12 volts. 5.8 volts at 700 milliamps gives you 8.28 ohms. So that's RC. To find RB, in the active region, I have beta IB is equal to IC. Depends on your textbook. Some textbooks call that HFE, times IB is IC. This is the gain. For the 6144 transistor, the gain is at least 300. So let's do worst case. IB ideally would be IC over 300. So 700 milliamps over 300 says this has to be at least 2.33 milliamps. That puts you in saturation. This is for the active mode. For saturation, I want to have more current. Beta IB is more than I need. And what I need is 700 milliamps. So pick beta IB to be bigger than 700, or IB to be greater than 2.33 milliamps. But it also has to be less than 25 milliamps, because that's all the pick can do. So pick a number bigger than 2.3, less than 25. I chose 10. In that case, RB then is, when the pick is on, 5 volts minus 0.7, 4.3 volts at 10 milliamps, 430 ohms. And there's actually a lot of room for slop here. That 10 is kind of a number I pulled out of thin air. I could make it less, make RB bigger, and it works. 1K works. 1K would be 4.3 milliamps. As long as it's bigger than 2.3, less than 25, this will work. Problem 6 looks at timing. Come up with a program to output D3 146 Hertz. Well, to do that, I need to find out how many clocks between toggles. So I want to output 146 hertz. This time right here is 10 million divided by hertz. That's the period. Half that because I want to set, then toggle twice, 2 toggles per cycle. So divide by 2. This is 34,052 clocks. One clock is 100 nanoseconds, or 10 megahertz. So come up with a wait loop that waits 34,052 clocks. Now, the wait loop I'm going to be using, this guy right here, the number of clocks in the wait is going to be the number of blue lines of code. That's 9, plus 1 for goto, 10. So it's going to be 10 times A times B, plus the red section, 4 lines of code, plus 1 for goto, 5, plus 5 times A, plus 4. So I want this to be true. 10AB plus 5A plus 4 is 34,052. One way to do that is, come back. The computer's fighting with me. Let's assume B is 255, the biggest it can be. So I've got 34,052. If B is 255, solve for A. So it's roughly divided by 10, divided by 255. A should be 13.34. Well, I can't do fractions, so let's round up. Let's say A equals 14. So trying again. I've got 34,052. Bring the 4 left, minus 4, minus 5 times A. 5 times 14. Subtract, divided by 10. Divided by 14. B should be 242.7. Again, I can't do fractions, so let's round up. Make B 243. So something that's close is 14 times 243. And if you try it, N is 34,094. A little bit off, but pretty close. 0.12% too high. That'll be my wait routine. So here's the code. I'm going to initialize. That is, make everybody output, everybody binary. I'm then going to increment port C, put the result in port C, then wait, and repeat. The subroutine wait is this guy. This waits 34,053 clocks. And if I try it, hitch up a speaker, so here's 100 ohms, going to my speaker to 100 ohms, 200 ohms in series with the speaker, keeps the current less than 25 milliamps. Measure the frequency with the piano tuner app. It's 146.5 hertz. It's supposed to be 146.83 hertz. So pretty darn close. With the sampler, I can play a precise frequency. Well, semi-precise. The last one is an LED flashlight. Come up with a program. And here's what that sounds like. Oops, wire fell out. So there's your little speaker. And if you try it, again, here's the piano tuner app. Almost dead on. Next problem is to build a flashlight. It should look like this. If I hit RB2, all the lights turn on. Then the lights start turning off every half second until all the lights are off. My port C pin 0 is not working. If I hit RB1, half the lights turn on. Then they start turning themselves off every half second, save the battery. Or I can sit there and manually turn it off. RB0 turns off all the lights. Okay, how do I do that? And all the lights are on. Then they start turning off. One light every half second. So to do that, I'm going to use this flowchart. Kind of helps to draw the flowchart first before we write the code. I'm going to make port B input, C and D output. I'm going to check the buttons. If I hit RB0, I'll turn off the lights. RB1, I'll turn on port D. RB2, turn on both port C and port D, then wait 500 milliseconds, then turn off one light, and repeat. So there's the flowchart. The way I'll turn off a light is I'm going to do a shift right. So what the shift right does, again, you can see from the lights here, the shift right command shifts the data to the right. It goes through the carry bit. When this bit right here carries over to port D, and then when I shift, I'm also going to clear port C bit 7. And a couple ways to do that. Probably just a bit clear port C bit 7 every loop is the simplest. So there's the flowchart. Now write the code. Kind of goes block by block. To initialize, that's this guy. Write FF to port B, clear, or tris B, clear tris C and tris D. That makes them output. Everybody binary. This is a label, label 1. And then when I check the buttons, if I hit RB0, bit test skip if clear. If I press it, I don't skip. I'll go to label 2. Check button 1. If I press it, go to label 3. If I press button 2, go to label 4. Otherwise, go to label 5. Label 2, I turn off all the lights, so clear port C, clear port D, go to label 5. Turn on port D, C is off, so I'll clear port C, write FF to port D, go to label 5. All the lights on, label 4, write FF to port C and port D. Label 5, I wait a half second, that sets the loop timing, and then I'm going to start shifting right. That's the rotate right through carry, port C, rotate right through carry, port D, and kind of what that does is there's a carry bit on the shifting. Port C shifts out, goes to the carry, that then goes to port D, comes in. I shift all the data through, and I want to shift in a 0. So either clear the carry bit of status, or it could also just say, just do a BCF, bit clear, port C, bit 7. And you get this effect. So that is homework set number 3 for 376. Again, a couple of people came in not really sure how to start. That's what flowcharts are for. Figure out the logic with a flowchart, then write the corresponding C code. Homework set number 3.